Hello dear students, this is your Jagan Sir. Welcome back to our physics channel, Physics with Jagan Sir. And we have successfully completed Newton's laws of motion, and after that we had started work energy power chapter. And in this chapter we had completed what is work done, how can we calculate work done in different situations, and different types of numericals also we have seen on the top. And the next one is work done by different forces, and out of that work done by kinetic friction. Work done by kinetic friction, and this concept I would like to explain with an example. See here, a 10 kg block is placed, m is equals to 10 kg. A 10 kg block is placed, right. A 10 kg block is placed on a rough horizontal floor. The block is being pulled with a by a constant force 100 newtons. 100 newtons, right, acting at an angle of 37 degrees. 37 degrees over displacement of 5 meters. That is, it is being pulled by 5 meters, and here f cos theta component will help, and this is the what is force applied. If the coefficient of kinetic friction between the block and floor is 0.4, 0.4, find the work done by the gravity. See here, the first question is, whenever we are solving work done, we have to use we have to use work done by individual forces. Now, work done by the gravity is, see, mg will act in this direction and displacement is in this direction, and angle between these two is 90 degrees. Now, work done by the gravity is equals to force due to gravity and displacement, that is mg cos 90 degrees. So, it will be 0. Work done by the gravity is equals to 0. First point. Then, work done by normal force. Normal is upward direction, and angle between these two, displacement vector and normal, is also 0. So, work done by normal is equals to normal and displacement, that is ns cos 90 is equals to 0. Then C bit, the applied force, work done by the applied force. See here, work done by external force F dot S. Now force and displacement have separated with angle 37 degrees, right? Now 100, displacement is 5, 4 by 5, 400 Newton, and the force of kinetic friction dV. Suppose this is the block, kinetic friction is acting in the leftward direction, Fk, right? Then work done is equals to Fk dot displacement, right? Fk is equals to mu n. Yes, angle between Fk and displacement vector is 180 degrees. So cos 180 degrees, which is equals to minus mu n s, and n value, see here, this is the f. So n f sin 37 mg. So let it be equation number 1. Along vertical direction, vertical direction, vertical direction, n plus f sin 37 minus mg is equals to 0. Then n is equals to mg minus f sin 37. N is equals to, mass is 10 kg, 10, 10 minus 100, 3 by 5, 20. So n is equals to 40. N is equals to 40, and substitute n value in equation 1. So work done is equals to minus mu value given as 0.4, 0.4, n value is 40, displacement is 5 meters. So this becomes minus 80 joules. Work done will be minus 80 joules, and this work done is by friction. So that work is being lost in the system. That's why we are getting answer in terms of negatives. That's why we are getting answer in terms of negatives, right? Chalo, next one. Suppose here a spring is present. This is spring, suppose, and if I am expanding the spring, obviously spring will try to pull the object towards its original position with the Fs force. That Fs spring force is directly proportional to the elongation, right? And this proportionality, next point is the spring force is trying to pull the object towards its mean position, and the spring force is opposing the external force, because whenever I am applying external force, the spring is trying to pull the object by opposing that external force. That's why we need to represent with the negative sign. And after that, Fs is equal to K minus X, where K is the proportionality constant or or spring constant so Fs is equals to minus Kx. Fs is equals to minus Kx. Now suppose let us consider xf, right? Now work done is equals to or minus Fs dot x, and see very carefully, minus Kx work done is equals to force into displacement. Here spring force is minus Fx dx cos, right, minus Fx dx, and xi to xf, then minus, one second, f value is kx here, kx, right, f is equals to minus fs dx minus no minus, right, fs dx, right, fs value is minus kx dx, right. Now minus k of x square by 2 xi to xef, then minus k by 2 xf square minus xi square, right. If xi is equals to 0, that means we are expanding the spring from its original length or natural length, then x f whole square, this is the amount of work done by the spring when it is elongation, when elongation takes place. Clear? Right. And based on this concept, let us go through an example. A block of mass m welded with a light spring of stiffness k, right, and is in equilibrium on a smooth inclined plane with angle of inclination theta. If a variable external force is applied slowly till the spring comes to its relaxed position, find the work done by the spring force. Now spring is already in compressed state. Let it be at this position in the relaxed state. Right. Now, see here, work done is equals to, and obviously mg sin theta will act like this. At a rest position, system is at rest position, and spring is trying to pull towards its mean position or relaxed position. So kx will act in the upward direction. I am taking only magnitude at rest position. kx is equals to mg sin theta, kx is equals to mg sin theta, then x is equals to mg sin theta by k, mg sin theta by k, right? Now see here, from compressed state to original position, relaxed position, the object is moving, so work done by spring in this case becomes positive, because from natural position to compressed or elongation stage we are getting negative value, but here the situation is opposing, that is from relaxed position, from compressed position to relaxed position it is moving, so work done will be positive in this case. By substituting 1 into substituting 1 in 2, work done is equals to half k x is equals to mg sin theta by k whole square. So it will be work done is equals to mg sin theta whole square by 2k, by 2k, right? This is work done by the spring. And next, work done by a pseudo force. And see here, pseudo force is a fictitious force, we know very well. A smooth block of mass m moves up from bottom to top of a wedge which is moving with an acceleration a naught. So the wedge is moving in this direction with an acceleration a naught. Find the work done by the pseudo force measured by the person sitting at the edge of the wedge. See, the block is moving like this from this position to this position, and when the block is moving in the upward direction, pseudo force will act in the opposite direction, mass of the object, acceleration of the platform, and this is what is the pseudo force. This is what is the pseudo force. And see, work done is equals to force into displacement, and displacement of the object is this one, and its length is given as l. Now work done is equals to force due to pseudo force ma naught in the leftward direction, and the displacement in the leftward direction l, and angle between force and displacement is 0 degrees. So work done by pseudo force in this case is ma naught l. Of course the object is moving in this direction, but on the x-axis, in the direction of force, the displacement of the object is l only. That's why we are considering here l, and this is what is the work done by the pseudo force, right? I hope I gave you the perfect subject on the topics which you are getting confusion, and if you need any assistance from my side, you can let me know through comment box. And for daily practice sheets and weekend examination papers, you can follow my telegram channel Physics with Jagan Sir. And next point is, if you need any extra material also, you can let me know. And before you are practicing your worksheets, better to have a look on my class notes and try to practice the questions which I am discussing on the board. Then only it will be very helpful for your practicing sessions, right? Have a great day. Take care. Bye bye.